Okay, so today we'll be talking about probability of compound events. Okay, now the probability of compound events is actually going to be dealing with some different situations. And as you can see, I have actually several different situations. Okay, so probability of independent events or the probability of dependent events. Okay, now there's some interesting things that do have to happen. And what we're going to talk about first is some of our vocab, and that's going to be mutually exclusive and inclusive. Okay, there are times where two events cannot happen at the same time, so that is going to be called mutually exclusive. Two events cannot happen at same time. Okay, so that would be mutually exclusive. Now, also another kind of reminder about how that works is that if you were actually able to make a Venn diagram and they have no intersection, that would be mutually exclusive. Okay. All right. Whereas inclusive is actually not mutually exclusive. In other words, they have some inclusive qualities. In other words, sometimes something could happen, it could be the same, but it just means not mutually exclusive. Okay? All right. Now, that's going to help a little bit later when we start talking about these two probabilities down here, but these two probabilities right here, the probability of two independent events. Independent events are events that their probabilities are not affected by each other. Dependent just depends upon the independent events that happen. Okay, and so there's some really interesting stuff. So let's start looking at some cards. Okay, there are 52 cards in a deck. Okay, there are 12 face cards. There are 13 cards per suit. Okay, there are, let's say, 4 suits, and you know the suits as hearts, spades, diamonds, and clubs. Okay, and there's 26 of each color. And this is one of the best examples to actually go through with some of this stuff. Okay. All right, so let's say that we wanted to do the probability of picking a king, then replace and picking a red card. Okay, so this is how you would actually write it out. Now, if you notice, we're replacing, so when we're replacing, it's an independent event. So what we're going to do is replace this with probability of getting a king times the probability of getting a red card. Okay, and then we can just focus on the actual numbers here. So this would be 4 out of 52. Okay, and then you would times that by 26 out of 52. Okay, now you could reduce each one of these first. I would probably reduce this to 1/13 times 1/2. Okay, to get the 1 over 26. Okay, so there's a 1 in 26 chance that actually happens. All right, now if we actually take this and get rid of this idea, okay, you pick a king and then pick a red card, okay, you're going to do the probability of getting a king first, then you times it by the probability of getting a red card following you getting a king card. Okay, so that probability is actually changed right there. All right, so if we go back to this, okay, all right, so the probability of getting a king would be 4 out of 52. That makes sense. But then probability of you getting a king, okay, this is going to be kind of interesting. This would actually be 26 out of 51. Okay, now it depends upon which king you actually have, so you might need to actually subtract some stuff from this and just actually be able to figure it out. So this one is a little bit interesting because now we have to actually multiply by a smaller fraction. So this will actually turn into 1 out of 13. Okay. And this one you might actually need to find a little bit different. We'll talk more about this when we get to conditional probability, because there is that possibility of getting a couple of different you could get a red king in the first card and then that reduces it, or you're getting a black king and then this would be right here. So if you're getting a red king, it would be 25 out of 51, and if you're getting a black king in that first card, you probably work with those together. So we would go 1/13 times 26 out of 51, and we would convert that to, that'd be 2 out of 51, which makes sense. Okay, now if it was the actual bottom part, it would be, oops, let's do 1 out of 13 times 25 out of 51. Okay, and that one would be 25 out of 663. Okay. All right, so it just depends upon which one you're actually working with. Now next we will actually work with mutually exclusive events, probability of, and probability of an inclusive events. All right, so let's take example dice. Okay, so let's look for the probability of 2 dice, and you roll a 4 or a, let's say, a 5 with them. Okay, now this would be an example of mutually exclusive. Okay, because the 4 and the 5 can't both exist at the same time, and they both don't affect each other. So you would take the probability of 4, rolling a 4, and then you would add that with the probability of rolling a 5. Okay, and the probability of rolling a 4 with one dice, okay, is 1 out of 6. And the probability of rolling with another die, 5 out of there, is going to be 1 out of 6 as well, which equals 2, 6, which equals 1/3. So the probability of that is going to be 1/3. Okay, now the probability of getting an ace or a red card when drawing 2 cards from a deck, or just from any kind of deck, okay, is, if you notice, this is actually inclusive. So that you would do the probability of getting an ace plus the probability of getting a red card minus the probability of a red ace. Okay? All right, and if we think about that, that's actually really easy to work with. The probability of getting an ace is 4 out of 52. Red card is 26 out of 52. And then minus, okay, a red ace, which is 2 out of 52. Okay, and if we add those up, 4 plus 26 is 30, plus 2 is 32. Minus 2 is 28, so this would be 28 out of 52, which would reduce to 14/26, which reduces to 7/13. Okay, and voila, you've actually worked with some of these. Now, the reason why we need to actually do this way, okay, mutually exclusive events, they're not going to be connected at all, so there's no overlap right there. Okay, so when you look at a Venn diagram of it, you're looking at a Venn diagram. Here's one event, and here's the other event, and they don't overlap, so you're not double counting anything. So that's why you can just add the two. Okay, however, with probability of inclusive events, okay, when you do a Venn diagram of it, they do have some overlap. So when you add this circle with this circle, you have double counted this middle part twice. So that's why you need to minus. It's almost like the little sliver in the middle. Okay, so that's why you add those two and then subtract it, because you double counted this once with this circle and then once with this circle. Okay, so that's why this subtraction part actually has to happen. Okay, and in conditional probability, like I said before, we'll talk more about what this actually means when we get to it. Okay, And just understand you might have to do two different situations to figure it out. And these decimals are really close together. I think this is about 3.7% and this is about 3.8% or something, okay? All right. That's it for working with probabilities of compound events. I'll talk to you later. Bye.